When we look at ecosystems and start to count the organisms inside, some have many blades of grass, others, lots of swamp animals, and sometimes an entire ecosystem can exist within a single living tree. Today we're going to talk about ecological pyramids. This is outcome 1.4K. So ecological pyramids represent the distribution of energy in an ecosystem, and they can exist in three different forms. A pyramid of numbers, which talks about the numbers of the organisms at each trophic level. A pyramid of biomass, where we talk about the biomass at each trophic level. And a pyramid of energy, where we talk about where the energy is contained in an ecosystem. So a pyramid of numbers represents the number of organisms that occupy each trophic level, and we can have many organisms in each level. So if we're looking at a prairie ecosystem, we can have grass, we can have trees, we can have crops, we can have lawn, we can have flowers, all at our level 1 producers. Our trophic level 2, or our primary consumers, also known as herbivores, can be snails, gophers, mice, cows, deer, anything that occupies that primary consumer role. Our secondary consumers, or our carnivores, omnivores, can be things as small as birds that are eating those snails and grasshoppers, all the way up to hawks if they're eating mice. Hawks also can be our tertiary consumer if they're eating those birds. Coyotes, they'll just fit in wherever they happen to fit in, depending on what they're consuming at the time. So there's one example where the number of producers is actually less than the number of primary consumers. And this is the case of where a forest with really large trees. So if you think about those old growth forests in BC, where one large tree can support many primary consumers. A pyramid of biomass is the dry mass of living organisms per unit of area. So we don't want to consider the water weight in each area. A pyramid of biomass indicates the mass present at each trophic level of an ecosystem. So even when we look back to that old growth forest where there's one tree supporting many consumers, that one tree's mass is still more than the consumers that are using it for energy. So here's a hypothetical biomass pyramid in an aquatic ecosystem. So our primary producer level is phytoplankton, followed by the herbivores, which would be zooplankton or Daphne or sea shrimp. Our low level carnivores would be shrimp, so again, a small. Then we have large fish and then a shark. So we can see here we have 1, 2, 3, 4, 5 trophic levels. And to fit any more, and we're losing a lot of energy in there. So like I said before, those aquatic ecosystems typically will have more trophic levels than terrestrial ecosystems. So pyramid of energy is where, again, we're going to talk about that 10% rule, where each step up the trophic level is going to be 10% of the energy of the lower level. So this one's really easy to draw mathematically because you have a 10% smaller one every time. So here, if we have 1 million joules of sunlight, we'll have 10,000 joules of energy in our plants. 1,000 joules of energy in our primary consumers, 100 joules in our secondary consumers, and 10 joules in our tertiary. To use other smaller numbers, we could have 150 joules of primary producers, 15 joules in our primary consumers or our second trophic level, 1.5 in our secondary consumers, and 0.15 joules stored in that muscle mass of our tertiary consumers. So you can really see here how after we get up to 4, maybe 5 trophic levels, that energy level drops so drastically. It's it would be hard for organisms to maintain the volume of food to eat to get the necessary energy that they needed. So there are advantages and disadvantages of the pyramids. The pyramids of numbers and biomass can sometimes be inverted due to certain situations. So like I said, for the pyramid of numbers, when you have a large tree and say like an old growth forest that can be inverted, there's a specific situation in a pyramid of biomass where there's an inversion. So if we talk about a plankton or algae bloom, all of a sudden we have a massive amount of primary our producers or our first trophic level, and then all those algae die. And so all of a sudden we have virtually no producers or our first trophic level. So that base will be really small, but there's still a large amount of zooplankton. And then the algae will grow again. But at that specific instant of time, we have a very small base of our pyramid. So these inverted pyramids then lose their ability to accurately predict the passage of energy from one trophic to the next, because we'll have a large amount of algae, a small amount of algae, a large amount of algae, a small amount of algae. So you'll see that as examples. So here's our inverted pyramid of numbers, where we have the one tree in the forest supporting many consumers because of its large size. And then here is that inverted pyramid of biomass with the phytoplankton. So we have a small amount of phytoplankton, and because they'll bloom and they'll die, but they'll always be reproducing itself. So they're always there to support the zooplankton, but the volume might not, or the mass of them might not always outweigh the zooplankton. Okay. But they do transfer a large amount of energy per kilogram of mass because we have that 10% rule. So here's again the different pyramids of biomass, where we have the primary consumers and versus the English Channel, the phytoplankton and zooplankton, as opposed to a terrestrial ecosystem where this one, for example, is in the Florida bog, where there'll be lots more permanent producers. Okay, so here's a pyramid of energy. Even though our pyramid of numbers is inverted, where it has that very small base, the pyramid of energy must always be upright. There must always be more energy at the first trophic level, or those producers, than there would be in the levels above it, because only 10% of that energy is transferred through each trophic level. So when we're looking at the disadvantages of the pyramid of energy, we must know exactly how much energy is contained in the tissue at each trophic level. So to know this exactly, we must use calorimetry. So this is when you take material, burn it, the water boils, we can see, or the water raises in temperature, we can see how much that temperature changed in the water, and we can determine how much energy was in that sample. But it's really time consuming to determine the exact values for a pyramid of energy. So as our climate changes, so will the distribution of organisms in our ecosystem. So we're seeing different crops being produced here. We're seeing the migration of different animals. Ticks are moving into different areas where they didn't used to be. Bears are migrating farther north or farther south, depending on the climate, so it's affecting their food sources. So if the organisms at the bottom of the ecological pyramid are affected, so if we have different crops being able to be grown in different areas, that change is going to be passed on up the food chain. If an ecosystem has fewer and less varied producers, so we're looking at taking a natural ecosystem and making it like a monocrop development. So if we have hectares and hectares of corn versus smaller crops grown in different areas, then the food web in that ecosystem will change, resulting in a more fragile ecosystem because we have less stability, we have less ability to survive changes in the environment because we only have one main producer at that level instead of several varied producers. So that's the end of our energy transfer in the ecosystem lesson. Thanks again for joining me, and I hope to see you again soon. Bye.
If you enjoyed this video, check out our website online.plrd.ab.ca and visit us on Facebook, Prairieland Online Academy. You can find out all that's going on with Prairieland Online Academy.